Okay, the moment you guys have been waiting for. How can we simulate gravity in space so that we don't have all these weird physiological effects that happen to the human body that would mess us up if we were traveling out there in space too long? Okay, so go to the slide that says faking gravity in space and read along with me. Living in zero gravity for too long takes a toll on the body. Biochemical research has revealed everything from weakened bones to misshaped eyes when astronauts return home from the ISS. Okay, maybe you guys heard about the recent twin study where they compared two astronauts, both twins, one that stayed on Earth, Mark Kelly, and then one that went up and spent a full year in the ISS, Scott Kelly, and they compared them physiologically afterwards to see how they were different. A lot of cool reading there if you guys want to get into that rabbit hole. And also a very interesting form of biomedical research that you might be interested in doing later on in life if you're interested in both medicine and physics. Okay, so hands down, the best way to do this would be to have a large rotating circular structure, right? So as it's moving through space, it's also rotating. And that rotation will create a centripetal acceleration that can then mimic gravity. So if the rotating circle has a diameter of 1.1 kilometers, what must be the rotation speed in revolutions per day to create an effect of Earth's gravity, okay? So you're gonna have something like this, right? Right, some like large cylindrical thing, right? And it's going to have these spokes, right? And it's going to be 1.1 kilometers or 1,100 meters in radius, right? Okay, and so what's going to happen here is that, there's going to be a fellow, an astronaut, a human person, right, that is walking around the outside of the sphere inside there. Obviously, it's going to be much, much bigger, right? It's not drawn to scale. But this rotating surface is he's going to be moving simply because there is a normal force pushing in on him, right? So that normal force is creating that centripetal acceleration, okay? Just like when you're walking on Earth, there's a normal force of the surface pushing back on you, right? And so the question is, what must be the velocity to create a centripetal acceleration of 9.8 meters per second squared? Okay. Well, we know that centripetal acceleration is really v squared over r, right? So really, the question is, what velocity will create that acceleration at this radius, which is, as you guys know, 1,100 meters, okay? And if I put that in, I get 103 meters per second. So it must spin at 103 meters per second, basically a soccer field every second. So this thing's moving, rotating up. One point here is rotating about the length of a soccer field or a football field every second, okay? But we don't want that. That's not intuitive, right? We want this to be in revolutions per day. How many times does this thing have to spin per day, right? And so, well, if I do just a little bit of unit conversion here, which you guys obviously know so well at this point, we know that one revolution is equal to 2 pi r meters, right? So those meters will cancel, okay? And that r is just the radius of this thing, which is 1,100, right? 2 pi r is the circumference of a circle. So in one revolution, I'm moving 2 pi r meters, right? One full circumference. And that's going to be multiplied by 3,600 seconds every hour, right? Times, so that seconds will cancel out with that seconds, times 24 hours in one day. Okay, so that cancels out with that. And my velocity then, in revolutions per day, is going to be 2,576, roughly, revolutions per day. Cool, huh? So if that thing spins in the course of a whole day about 2,500 times, you're getting a pretty close facsimile to gravity, which I think is neat. There is many, many science fiction movies now that show this effect. A very good classic is The Martian, so maybe go check that out. Otherwise, that is what I have for circular motion this week. And if you guys have any questions, don't hesitate to reach out. If you need other resources, don't hesitate to reach out. And I hope this was interesting. I'll see you next week.